So when I was asked to talk about serological tools, I thought, oh my lord, I could be talking for about 2 or 3 hours to begin with, just to even cover everything. So what I'm going to do is put it into context with antibody identification. So what I'm going to try and cover today is I'll define what immunohematology problems are, and that is in the context of this presentation, because there's going to be loads more that I won't be covering. And then I'll talk about complex antibody investigations, how we choose the appropriate tests with these types of cases, and this will bring in the supplementary serological method. So I'm not going to be covering routine methods because that's been done this morning. This is tests when routine tests can't work out the answer. And then I'm going to try and tie it all together with a case study, because I think that really is the best way to see these tools in action. And then just a summary and some final comments about these tools that we have. So when we're talking about serological testing, the basis of this testing is detection, reading, and interpretation of hemagglutination. And this can be in a direct test, which is often for IgM antibodies, or it can be in an indirect way, such as the indirect antiglobulin test, which is the gold standard, really. And that's for the IgG antibodies. But there are other things as well, like ELISAs. There are now many vehicles for detection, and they come in automated and manual forms. Now, I'm not going to be specifying a specific IAT method, but at the IBJRL for our complex cases, our routine method is a list tube technique. So when we're talking about immunohematology problems, these problems are usually identified during routine pre-transfusion and antenatal testing, and they need additional tests other than the routine methods to resolve them. And usually they need referral to a reference laboratory. And these can take the form of phenotype discrepancies, and this can be patients and donors, and also antibody identification. And when we talk about antibody ID, this could be complex mixtures of antibodies, or antibodies to high-frequency antigens, or autoantibodies. They all need to be resolved in order to make informed clinical decisions. So I'm going to be covering the complex mixtures and antibodies to high-frequency antigens today, because these areas are where blood provision may be quite difficult. So when we're talking about complex antibody investigations, we really do need to use manual serological techniques. And the initial testing provides those first clues as to which direction we need to go with these techniques. And it goes without saying, really, that the knowledge of antigen and antibody characteristics are very important for being able to recognize those clues. So I'm talking about modes of reactivity. What temperature is the antibody reacting? What method? Is it direct, indirect? And also, is there in vitro hemolysis? Things like that. Obviously, experience gives a distinct advantage when it comes to that type of knowledge. And I believe that one of the biggest tools is passion for wanting to solve puzzles. That's what you need when you're looking at complex antibody identification. So as an example, I have just put up a panel here, and this is one method, untreated cells tested by the indirect antiglobulin test. Now, at first glance, you would say all cells are positive. This could possibly be an antibody to a high-frequency antigen. There's variable reactivity, might be a mixture. But if you just add 2 tests, a papain IAT test and a direct agglutination test at room temperature, you can automatically see that you are dealing with at least 3 different antibodies. So you have something that's papain sensitive, and something that's possibly enhanced by papain or reacting in the same strength as papain, so there could be 4 antibodies. And then there's something there that's reacting at 18 degrees. And I think it's different to the one that is papain sensitive. If you look at cell 4, it's a strong reaction, but there's no reaction at 18 degrees. If you look at cell 6, it's a weaker reaction, but there's a reaction at 18. So it looks like it's a different antibody because the strength isn't comparable. And then the other area where knowledge of antibody characteristics is key is when we're looking at antibodies to high-frequency antigens. So I've given 4 examples here of different reaction profiles that we might see when we're looking at antibodies to high-frequency antigens. Now, in each of those situations, all the cells are positive, but you can see that it's a very different picture for each scenario. And in the panel number 1 there, you can see something that's papain sensitive and showing variable reactivity. This is a classic picture for something like anti-Cheeto Rogers or an anti-Knox McCoy. And then in number 2, you've got a much more consistent reactivity strength. Again, papain sensitivity. So that papain sensitivity really does cut down the amount of specificities that you could be dealing with. And this is a classic picture for anti-JMH or IMB, Gerbish2, YTA. Number 3 can fit quite a few specificities. And we've got consistent strength, and it's strong in papain as well. I've put just a few systems there, but this one, there are quite a few options. I would say, though, with RH and Dombrock especially, you probably see some enhancement in papain. And then with number 4, we've got hemolysis in the papain test, and we've got a strong antibody reacting in the direct agglutination test as well. And this is often seen with strong examples of anti-VEL and also anti-PEP1PK in little P people and anti-H in Bombays. So just by doing a few different techniques, you can get those initial clues instantly. So the next stage is to look at what the pattern looks like. You need to know what the patient can make. This is crucial at this stage. You can't really go any further without knowing the patient's phenotypes, the common antigens, because you're going in blind otherwise. So you need to establish the patient's phenotype, and then you need to include an antigen-matched cell. So if this cell is negative with the patient's plasma, then you are most likely dealing with a mixture of antibodies to routine antigens. So you then need to go on to do systematic inclusion and exclusion of antibodies with additional cells. If additional cells aren't available, then another tool that you can use is differential alloabsorptions. And this can be used when panel cells are in short supply. If these cells are positive, then you are most likely dealing with an antibody to a high-frequency antigen. So when we get to this stage, we need to start thinking about using some of our supplementary serological tools. So the options are to type the patient's cells for selected high-frequency antigens, or to match selected null cells, so they're negative for high-frequency antigens. And I say selected because there's no point just testing for everything. And you select what you're going to type for, or which cells you might match with, based on that initial pattern of reactivity that you've seen and that we've discussed already. And at this stage, there are also some other useful indicator cells that you could test the patient's plasma with. In Lu cells, which are the dominant type of Lutheran A neg B neg cells, also they have suppression of Lutheran antigens, but they also have other antigens in different systems suppressed as well. So a negative or a weak reaction with these cells can be a good indication of what you might be dealing with. Cord cells also have weak or negative for some antigens, and the majority of them there are weak or neg, but the N2, the LW and the Li, it's actually enhanced on cord cells. So again, it's a really good indication what you might be dealing with. And I've put C4 coated cells there, and that's artificially C4 coated cells, which is very easy to do. You just use fresh AB complement and sucrose. And this is an excellent indicator for if you think that you're dealing with an anti-Cheeto Rogers antibody. If you coat the cells and test them in parallel with uncoated cells, you would probably go from, say, a 1+ reaction with uncoated to a 5 with coated cells. And it instantly tells you that you are dealing with anti-Cheeto Rogers. So from this set of tests, if you have a clue from those tests, you then need to go on and confirm with additional cells and sero if it's available. So if you were to find that patient cells were negative for a high-frequency antigen, you'd need to confirm that using controls, and then you could match the cells that are negative for the high-frequency antigen. And this is to then go on and perform exclusions of any underlying alloantibodies. If there isn't a clue, This is where we get to have some fun and get a bit creative with the next steps and the next tests that we can look at using. So one of the first options is to make an elevate off of group O antigen matched cells. Now again, you need to know what the patient's phenotype is. And this is going to be a recurring theme as we go through these slides. So if you absorb the patient's plasma onto these group O antigen matched cells, you elute off the antibody, and you then eliminate the ABO problem. So you might be able to match null cells that were ABO incompatible with the patient's plasma without having to worry about that. And it isolates the antibody to high-frequency antigen. So again, you don't have to worry about any underlying alloantibodies to common antigens. We can also use inhibition studies, and Cheeto and Rogers antigens are plasma antigens, so they're present on C4 in your plasma, and plasma can then be used to inhibit anti-Cheeto and Rogers. You can also use plasma from Cheeto negative Rogers positive individuals or Cheeto positive Rogers negative individuals to specifically work out whether it's anti-Cheeto or anti-Rogers. It's really not needed to clinically to know what the specificity is between the two, because it's not a significant antibody. And then something that's quite exciting, I think it's going to really come into its own when it is fully validated for possibly cross-matching, is soluble recombinant blood group proteins. They're very, very useful, especially for CR1-related antibodies. And they're also very useful when dealing with complex mixtures containing an antibody to a high-frequency antigen. And you use very, very small amounts. It's about 6 microliters to 50 microliters of the patient's plasma. And you use these proteins in an inhibition in parallel with a diluent control. So you do the inhibition phase with the soluble recombinant protein, and then you have your DIL control. And if you have a positive DIL control and a negative inhibition test with the soluble recombinant protein, then you have proven that you are dealing with that protein and antigens in an antibody to an antigen in that system. Now, one of the tools that we swear by at IBJRL is the use of enzyme and chemical modification of cells and then testing the patient's plasma. You can instantly get a clue as to what system you might be dealing with, and I've highlighted chroma here because that's a very distinct pattern. It's almost unique to chroma. So if you were to get a pattern like this, you would be able to then go down the track of chroma. Now, the Maya is quite a labor-intensive assay. It's an ELISA assay. It's a monoclonal antibody immobilization of erythrocyte antigens, which is why we shorten it to Maya. It's very useful when a particular blood group is suspected, and this is usually based on an enzyme study. So you may have done your enzyme panel and thought, well, I think that it's this blood group system, but you've typed all the cells for all the known and high-frequency antigens in that system and haven't got a negative. So you could be dealing with something new in that system. So you can use specific monoclonal antibodies for the protein that you suspect, and you incubate it with the cells and the human sera, and if both the human antibody and the monoclonal antibody bind to the same target protein, then you're going to get a positive result in the Maya, because we release the trimolecular complex by solubilizing the red blood cells, capture it on a plate, and then detect it. It can also be very useful as a competitive binding assay. If you use monoclonal antibodies that are directed to different parts of the protein, and if you get, say, 2 positives and 1 negative, then that's an indication that the negative, where the negative monoclonal is directed towards, that's probably where the same region where your patient's antibody is directed. In the IBJRL, we currently use the Maya for CR1, which is the NOPS, Cal, Lutheran, Chroma, the Indian system, and Cartwright system. And it's very, very successful. It's actually helped us to discover the new antigens, Lutheran 21 and IN3 and IN4 in the Indian system. The Maya was how we were able to solve those cases. Now, I know I'm supposed to be talking about serology, but I think in this day and age it would be quite remiss not to mention molecular techniques in context of serological testing, because I think where we used to maybe think that the molecular techniques were the enemy because they're going to take over what we were doing, they now really are part of the immunohematology laboratory repertoire, and we need to get to grips with the molecular techniques that are available to us and exploit them, because they now go hand in hand with serological techniques. So I'm going to bring this all together with a case study, and I will warn you, I've chosen a case study that we used nearly every one of these methods in, so it's quite a complex one, but it's very interesting. This case was a UK referral, and it was a 64-year-old female patient with rheumatoid arthritis, and she was anemic, and they wanted to transfuse her. The referral lab was kind enough to give us a full phenotype, so we had that information already. And they said that the plasma was positive with all panel cells, and the DAT was negative. So they thought that they were dealing with an antibody to a high incidence antigen, and so it got sent to IPGRL. So this was our first panel, and I think you can agree that instantly we can tell that we're dealing with a mixture of antibodies here. So if we look at cells 4 and 6, we identified these reactions here at 18 degrees as anti-M. It was very strong, but it was very evident. And then if cell 3 here, you can see there's a stronger reaction in the untreated IAT test, and there's some reduction in papain. This indicated that anti-Duffier was there, but there was also something else, and it was reacting quite consistently. Of course, there could be more than one thing, but it looked like something that was papain resistant, and it was reacting with all the remaining cells. So the next step with this type of test would be to test a panel of antigen match cells, so for the patient's common phenotypes. So we did this, and they were all incompatible, and they were, again, that same consistent strength of reactivity and papain resistant. So we decided, because of this issue with what appeared to be multiple antibodies, we would type for high incidence antigens. And we got a negative. And we thought, oh, great, we've solved it. Just put up some JRA negative cells and it'll be done. So the panel of JRA negative cells that we had available was a bit limited because of the additional antibodies present. They were all Duffier positive. So we had to prepare an eluate. So we used group O antigen match cells and isolated the antibody to high frequency antigen, and then tested the panel of JRA negative cells. But they were all positive. So we thought, oh, okay, it's not over, so we're going to have to keep going. There are some possibilities here. The patient might not actually be JRA negative. We could have made a mistake. So we checked the JRA type with 3 examples of anti-JRA, and the patient was definitely JRA negative. It might not be JRA. They might be JRA negative but not made anti-JRA. It could be anti-JRA plus another antibody to a high incidence antigen that is papain resistant. So what we decided to do was our enzyme study using JRA negative cells and JRA positive cells, antigen matched JRA positive cells. And you can see quite clearly from this pattern that there are 2 antibodies present. The JRA positive cell is giving the pattern that we would expect for anti-JRA. The JRA negative cell is showing a much different pattern of reactivity. There's trypsin and chymotrypsin and pronase sensitivity here. And this was instantly able to tell us that we were probably dealing with a Lutheran-related antibody and or anti-MER2. So the next steps were to type the patient's cells for known Lutheran high-frequency antigens and MER2. Now, we had already done the Lutheran B type in our initial screen when we found that the patient was JRA negative, so we knew it wasn't that. But they were all positive, and we typed for all of them because we have those antisera. So we decided then that we needed to do an adsorption and elution using JRA negative cells to isolate the antibody to unknown high-frequency antigen. And of course, we're limited by the amount of rare cells we have to do the absorption and elution. We don't want to be using up vast amounts of rare cells to do this, so we had to use the minimal amount. And the problem was that the only JRA negative cells that we had enough of were Duffier positive. So we decided to go ahead anyway because the papain test in this situation would be key. Even if we adsorb and elute anti-Duffier in addition to the antibody to high-frequency antigen, if there's a negative test in papain, then that would indicate that it was probably Lutheran or MER2. At the same time, we decided to do the Maya assay. Because of it being such a complex case, we were throwing everything at it. And we decided to use 3 monoclonal antibodies, and they were tested on 1 plate, and they were all positive. So we knew instantly that we were right. It looked like it was going to be a Lutheran specificity. And there was no competitive binding, so because the monoclonal antibodies, we knew where they were directed towards on the protein, we were able to sort of make a prediction that the antibody wasn't directed to an antigen in those regions, because it had to have bound to somewhere else. So we went on to test the elute. Again, we were limited because we had to make a very small amount, so we had to be very selective about the cells that we tested. And we decided that we needed to test the in-lieu cells. So these are the ones that I've already mentioned about being good indicator cells. And they're the dominant type of Lutheran A neg, B neg, and they suppress all Lutheran antigens plus other antigens in different systems that are highlighted there. And then there are Lutheran A neg, B negs of the recessive type, and these are homozygous for a recessive allele at the Lutheran locus. So they have no Lutheran antigens, but they don't have this weakening or suppression of other antigens in the different systems. They are extremely rare. I think we have 3. And this is the results of that testing. So I hope you'll agree that it shows it very nicely that we have eluted the anti-Duffier, which is stronger there, untreated IAT, but we have also eluted a Lutheran-related antibody to high frequency. So the weak reactions with the in-lieu cells are due to the fact that they are not negative for Lutheran antigens, they are weak. And this antibody is actually picking up that weak Lutheran antigen on those cells. The recessive Lutheran A neg, B neg is the key test here, because we have a negative result in papain, and this indicates that we are dealing with a Lutheran specificity, and we've had to rely on the papain test to prove that. And then the bottom cell, the Lutheran pos Duffier neg, is just showing how the Lutheran antibody is reacting. So we went on to sequence the patient's DNA for the Lutheran gene. All 15 exons were sequenced. And we found that the patient had the Lutheran B genotype, but in addition, they had a novel homozygous mutation found in exon 12. And this was projected to give rise to the lack of a novel high-frequency Lutheran antigen. So to summarize this case, we found that the patient had anti-M, anti-Duffier, anti-JRA, plus an antibody to a novel Lutheran high-frequency antigen. And the presence of 2 antibodies to high-frequency antigens, especially with one of them turning out to be novel, made this investigation very complex and time-consuming, but also very fun. We had limited amounts of plasma, so it also required a bit of tactical thinking, because you sometimes can't get another sample from the patient, and in this case, we couldn't get another sample from the patient. And I think this case highlights that molecular testing now plays a really important role in the resolution of complex serological cases such as this one. So my final comments really to say that I hope I've shown that the investigation of complex serological problems must be carried out in a stepwise, informed way to ensure that the minimal possible delay in patient care is achieved, and also that you conserve very rare reagents. Knowledge of antigen and antibody characteristics is fundamental to recognizing those clues when investigating complex immunohematology cases. And although there are many tools at our disposal, unfortunately, serologists skilled in manual serological techniques are becoming a rarity. It is important also to embrace the molecular tools we now have at our disposal in the immunohematology lab and to achieve an optimal approach to solving problem cases using both molecular and serological techniques. Thank you.